Good morning. Today we finally get to talk about refraction. Refraction, not reflection, but refraction is when light enters or leaves a material. And this material obviously would have to be a material that allows light to travel in it, something that we would call transparent or at least translucent. Um, Bricks not known for their transparency, so light doesn't penetrate that far into a brick before it is stopped, absorbed, or otherwise um, uh, suffers consequences. So let's talk about a transparent material that we're very commonly using around here. Let's just talk about glass. So let's zoom in. Here's the window in your bedroom. You got the panes and all this kind of stuff. We're going to zoom in to when some ray of light from the sun hits the glass of your window. And in fact, I want the ray of light from the sun. Let's not have it from the sun. Let's have it from a flashlight or a set of headlights outside. I want it to hit straight. So if we zoom in on that, there's a line. We're on this side. We are in air, and on this side we are in glass. And let's ignore for the moment that air is itself a material that light would be in. Let's just pretend that air doesn't exist for now, just to set up the situation. So a piece of light with its attendant wavelength and all wave properties and its ray type properties hits the glass and enters the glass. The question is, what does it do? And the answer is light slows when it enters materials. Okay, we talked about how light is a self-propagating electric and magnetic field, and that because there's no mass involved, this is a really fast process, flipping back and forth between the electric and magnetic fields. But if you're in a material, there's going to be some resistance to the buildup of electric and magnetic fields because the material is made of atoms, and atoms have electrically charged components. So necessarily, light is going to slow down. So when it slows down, what's going to happen to it? Well, the truth of the matter is that it's going to bunch up. And I'm using a different color here because I want you to see that I'm drawing this with a shorter wavelength. So one of the things that's going to happen is the wavelength is going to decrease. The frequency, however, stays the same. The same number of waves that hit this boundary continue on into here in a given second. So this frequency is the same, but the wavelength has changed and the velocity has changed. So our wave equation, V equals lambda F, can still be true because we're going to have a decrease in velocity and a decrease in wavelength. How much does the velocity decrease? Excellent question. We have a formula for that. The velocity of light in any material is equal to the velocity of light in a vacuum divided by some number. And this number is called the index of refraction. And the index of refraction is a number greater than 1, because we're going to be dividing the speed of light in a vacuum, which is 3 times 10 to the 8 meters per second. We're going to be dividing it by a number to get a slower number. We're never going to divide by a number less than 1. We're never going to get a faster number. So let's talk about this. Let's make a table. What are some materials that you may want to pay attention to, and what are their indices of refraction? Well, the first material we can talk about is a vacuum. The complete lack of material has an index of refraction defined as 1. That means that the speed of light in that material is going to be c, 3 times 10 to the 8. Then there's air. And air is a very thin gas, surrounds our planet at various thicknesses, and it has an index of refraction of 1.003. So that's 0.3% different than a vacuum. So a reduction in speed of 0.3%. And if I get my trusty handy dandy calculator out here, and we take 3 times 10 to the 8, and we divide by 1.003, we get 2.991 times 10 to the 8 meters per second. So that's very little difference. Now, another thing that light travels through that we have here on Earth is water, and water has an index refraction of about 1.33. Now 1.33, that's 33% So 3 times 10 to the 8 divided by 1.33. Why, we're down to 2.26 times 10 to the 8 meters per second. A couple more here for you. One is glass. Now, glass, there are many different types of glass. There is more than one formula for glass. Uh, Different types of glass. For example, you understand that the glass in your window at your house and the glass that covers your cell phone have different chemical compositions because have different behavior. The glass covering the cell phone is significantly stronger and resistant to scratches. However, it does have a flaw. The Gorilla Glass on your cell phone doesn't handle being hit from the side very well, and so that's when it gets cracked. When you drop your phone on its edge is the problem. Glass in general is about 1.5, and that means that I believe if we do this, I believe we're going to get down to 2, but let's do this. 3 divided by 1.5 equals, 2 times 10 to the 8 meters per second. And the last one I'm going to do is another transparent material, which we are going to talk about at the end of this lecture series, and a diamond. Diamond has an index refraction of about 2.4. Let's do one more. Let's do Lucite. Lucite is plexiglass. That is the plastic glass that's used sometimes as bulletproof glass, or they're putting these shields up between you and cashiers everywhere, and it has an index refraction about 1.7. But if we do the speed of, actually, I'm going to ask you to do this. I want you to use this formula here in red to calculate the speed of light inside of a diamond. That's your little homework for this lecture. Okay, so we know that when light enters a new material, it's going to slow down and its wavelength is going to shrink. One way to think about this, by the way, and this is fun, and we'll use this later, if you don't like the wavelength hump type argument, what if we imagine that this wave is a marching band? And so as seen from the top, these dots represent different players of instruments, and they're all spaced out from each other and they're marching. Well, as they're moving in this direction, the first row of marching band members crosses over into this slower material, and let's just say if these marching people are on concrete, and then this is sand at the beach, why, they're going to slow down, and so they slow down, and as they slow down, the next group is able to catch up to them because the second group is still in the concrete when the first group is in the sand. And so when they enter the sand, they're going to be much closer. And then this group catches up to the second group. And when they enter the sand, they're much closer. So the marching band analogy is another good analogy for how this works. Now, there is a video out there that indicates that these models for what light does, they're all flawed in some way. And I would agree with that. Most models are flawed in some way. Most analogies somehow oversimplify things. And if they miss an important concept, they're going to lead you to the wrong conclusion. The idea is to wrap your brain around the idea and then to actually just understand the idea. Okay, so now that we know that things slow down and that their frequency changes, I'm going to make the argument that refraction is also bending of light. So let's talk about this interface between the air and the glass. And let's now have a ray of light from the sun hitting the glass of your bedroom. And I'm going to dispense with the wiggly wavely things. And it's going to hit here and it's going to enter the new material. And not only is it going to slow down, but I submit that it is going to bend. And it is going to not continue along the direction it used to be going, but that it is going to bend this way and turn. There will be a discontinuity at that point. Now, in order to do this and to talk about it, we're going to measure everything relative to a perpendicular line, perpendicular to the interface, that is called the normal. And so what we're going to have here is when we go from a fast material into a slow material, we are going to bend towards the normal. Now, one of the ways that you can see this is kind of the marching band model or maybe a car model. Let's just do this. Let's pretend that we have ourselves a fast surface for cars, And here's a car, and it is heading towards a slow surface, like some deep mud. Now, what's going to happen to this car? Well, what's going to happen is that this left front wheel is going to be the first one to transition into the slow material. So the left side of the car is going to slow down before the right side does. And if the left side of the car slows down before the right side does, that's going to turn the car, and the car is going to actually reorient itself this way. It's one of the reasons they have a sign on roads saying danger, soft shoulder, because when you go to pull off the road on those things, your car twists and turns, and you have to fight that with the steering wheel, or you will find yourself far from the road surface, perhaps in a ditch or through a fence, staring at somebody's cow. So when you go to get off a road onto a gravel or sand soft shoulder, you need to do so at a slow speed and with lots of control and ready to counter steer for this reason. So going from a fast material to a slow material, we're going to bend towards the normal. If we were, for some reason, going from a slow material to a fast material, like let's say, for example, here's some water in your pool, and here's some air, and you are hiding in the pool, not to scale, with a laser pointer, and you decide that you are going to shine the laser pointer at some bird that might be up here. Check out what happens. All right, so your laser, we'll make it a green laser. We're not gonna. You're aimed right at the bird. It's gonna hit the bird. Oh yeah, you're good. And then what happens is when it reaches the boundary, it's going to bend away from the normal because we're going from a slow material to a fast material. And so the laser actually misses. So this angle inside the material is much smaller than the angle outside the material. I for incident, R for refracted. And it's this very reason that people have trouble figuring out where things are. For example, if you were a caveman and there was a fish inside the water, and you had your spear in your hand and you were getting ready to spear you up some little fishy, it turns out that the light from the fish that would get to your eyes actually started life headed well above your head, but then because of this refraction and bending away from the normal, the light goes into your eyes after bending at the surface. Now you, unfortunately, you think that the fish is back along this line, so you think that the fish is over here. And so you throw your spear over there, and unless the spear refracts like light does in the water, you're not going to hit the fish. You're going to miss it. I sometimes I tell a story about trying to fish a quarter out of the fountain inside of South Coast Plaza when I was a kid, and missing. My hand missed the quarter that I could see, and that's the first time I personally learned about this. There is, however, a scene in the movie Castaway where they're trying to show the passage of time and the fact that Tom Hanks has learned to master his environment, and they do so by showing a fish swimming in shallow water, and then Tom Hanks is able to spear it, which means that he has dealt with this situation, learned how to overcome it, and found himself a way to get some sort of dinner, lunch, or otherwise. As I recall, he just eats the fish like raw. I don't know. Don't you want to scale it first? I don't know. Maybe if you're hungry, you're hungry. Okay, so what can we do with this? Well, let's talk about some stuff here. First of all, let's talk about a block of glass that is parallel on each side. And now, if we bring in a ray of light, let's make it green light, and we bring it in like this, directly along the normal, it's not going to bend left or right, because when you come along the normal, you stay along the normal. It's only when you're off of the normal that your angle changes. So the light is going to come straight out the other side and be unaffected. This is the reason why we make our windows out of parallel-sided panes of glass. That's the important thing about a pane of glass. And if you've ever been to a really old house where the windows weren't constructed as well and the sides of the glass aren't parallel to each other, you can see some distortion when you look out that glass. Now, what about if we had the same parallel-sided pane of glass, but we brought the light in at an angle? I'm going to tilt the glass instead. Okay, well now there is an angle between the incoming light and the normal, and so what's going to happen is the light entering the slow material is not going to continue in its same direction, but it is going to bend a little closer to the normal. So we're going to go down this way, and then when it goes to leave the glass, there's another normal over there, but it's parallel to the first one. And now we're going to bend away from the normal, and so it's going to bend back to its original path. So although it's been shifted down a little bit, it still is in the same direction. And so things, when you look through tilted glass, do look pretty much the same as if you look through straight glass. Okay, so that works pretty well. But let me be clever here. What if I made a piece of glass that was triangular in shape? And I brought a piece of light into this triangular shaped piece of glass. Like that. Okay, now we're hitting a tilted surface like we were there. And so the light, instead of continuing straight, is going to bend down towards the normal a little bit. So instead of straight, it's going to bend down this way. But now when we go to leave the glass, the normal is in a completely different direction. Over here. And now, because we're going from a slow to a fast material, we are going to bend away from the normal, which is bending down even further and coming out with a very large angle. So we've turned once on the way in and once again on the way out, but not back to our original path because the two sides are not parallel to each other. We've turned, continue to turn in the same direction. So a triangular shaped piece of glass will bend light towards the fat side of the glass, not the pointy side. And you say, well, Harmon, what are you doing with that? Oh, how about this? How about I stack on top of each other a triangular section, a parallel-sided section, and another triangular section. And I bring into this particular structure, I bring 3 parallel rays of light, like you might get from the sun or your face if you're sufficiently far away. Well, with the 2 refractions that happen on the top, this ray is going to come out headed down that way. The 2 refractions that happen on the bottom is going to be towards the fat side, which is upwards, and this one's going to come out this way, and this one's going to go straight through, and we have ourselves another focus. This is a lens. This is a magnifying lens. This shape, especially if I was to make it instead of out of discrete components, but out of a continuous shape that's fat in the middle and skinny on the ends, is a convex lens. And a convex lens converges light to a focus or focal point. And yes, if you ever had a magnifying glass as a kid, you could take the parallel rays of light from the sun and you could get them to all focus down. I'm gonna pretend that the bending happens in the middle of the lens. I know it happens some at the front side and some at the back side, but let's just have it do this. Oh God, Harmon, you are a magnificent artist. Anyway, these rays of light all go through a focus. And if you put a leaf right there, you can start a little fire. There you go. Well, wait a second, hold on. What if I was to do something a little different? What if I was to create an upside down triangle, a parallel sided shape, and an upside down triangle? What would this structure do? And I'll use the green pen again. So here we have a ray of light that comes in straight to here, and straight to here. This one's going to bend away from the point towards the fat base. This one's going to bend away from the point towards the fat base, and this one's going to go straight through. This kind of light, that's really interesting. This kind of lens, excuse me, is fat on either end and is a concave lens. This kind of lens takes parallel rays of light and diverges them, spreads them out. No focus. So this diverges light. Away from a focus. Wait, what do you mean away from the focus? Hold on. Well, check it out. These rays of light are diverging, and they all appear to have come from some place back here, which could be considered a focal point, although the focal point's on the other side of the lens. As it turns out, lenses have two focal points, one on each side, and we're going to be able to draw the same rays we did for mirrors, and we're going to be able to find images from lenses just like we did with mirrors, and that's the subject of our next lesson. So thank you for your attention, and we'll catch you on the flip side.